So far we have discussed the theory behind the correlations for flow over a flat plate, an isothermal flat plate. When I referred to table 7.1 previously, I meant table 7.9. So this is table 7.9, provides many correlations. The first several are all associated with a flat plate. So there's the geometry column, all referring to a flat plate, and these are all for an isothermal situation, so an isothermal flat plate. Correlations over here give you local values or average value accordingly, and then the conditions for the flow are specified in the far right, so laminar or turbulent or mixed in this case for the average. So you have friction coefficients average and local, Nusselt numbers average and local for laminar and for turbulent, and then for mixed flow the average for the Nusselt number and the friction coefficient are provided as well. So we've already talked about the theory behind all of these. Now let's work a few examples that apply these. These examples come from previous exams and are in the sample problems I've provided for you. Okay, so air at 27 degrees, 1 atmosphere flows over a flat plate. It's coming in at 30 meters per second. The plate is heated to maintain a uniform temperature of 60 degrees C. Determine the local heat transfer coefficient at a distance of 20 and 40 centimeters from the leading edge, and then find the total heat transferred over a 40 centimeter long plate. In this situation, it happens to be 15 centimeters long. Rather than write everything out, I'm going to continue to just show you my solutions and talk through the solutions, but you'll have to understand it'll take you much longer if you are writing all of this out. Okay, so to identify the problem, it's flow over a flat plate. So here's my drawing of the flat plate. The temperature of the plate is 60 degrees C. T ambient is 27 degrees C. I'm identifying that this is air, is the fluid. U ambient is 30 meters per second passing over this. It's asking for the local heat transfer coefficients at a distance 20 centimeters and then again at 40 centimeters from the leading edge of the plate. And then it wants to know what is Q for a plate that happens to have a total length of 40 centimeters and then a width into the page of 15 centimeters. The first thing I would do is go get appropriate properties, which means you need the film temperature. So TF is the average between T surface and T ambient. In this case, 43.5 degrees C, 316 K. So you need to go to the tables for air. That is table A4. There are columns for kinematic viscosity, K. There's also a column for the Prandtl number. Remember, Prandtl number is nu over alpha. Both of those properties depend on temperature, and so the Prandtl number will also depend on temperature. So you have to do some work to interpolate properties. Do not just use properties at 300, or do not fail to interpolate. Those correlations depend on temperature through the property values. It's even pointed out in table 9 that the correlations are based on T film. That's how important it is. The table makes sure it explicitly tells you that they're based on the film temperature. So calculate film temperature, go get the property values. Then the next question is going to be, where does the plate transition from a laminar flow situation to turbulent? So let's calculate the critical distance. Critical Reynolds number 5 times 10 to the 5th, so solve that for x sub c. Nu over u times 5 times 10 to the 5th. Substitute in numbers, be careful with units, 0.29 meters or 29 centimeters from the leading edge. So we have a situation in the first case where we're 20 centimeters from the leading edge, so that'll be in the laminar region. At 40, it'll be beyond this, so it'll be in the turbulent region. Alright, so for the first one in the laminar region, We're going to use a Nusselt number correlation so we can read that off the chart. 7.9 again. Laminar. Nusselt number, so this is the correlation I'm using, 0.332 Reynolds number to the 1/2, Prandtl number to the 1/3. 0.332 Reynolds numbers to the 1/2, Prandtl number to the 1/3. Definition of that Nusselt number, right, is H times X over K. So solving that for H, you get K of the fluid over X times the Nusselt number. So we're going to evaluate this at X equal to 20 centimeters. For that Reynolds number, the Reynolds number, remember the definition of the Reynolds number is, let's put it over here, the Reynolds number based on X is defined as U ambient X over kinematic viscosity nu. So if you substitute 20 centimeters into that, 3.419 times 10 to the 5th. So put this in place here, put the Nusselt number in place here, solve for H, 23.77 watts per meter squared K. Do the same thing again for the turbulent flow, except that we need a different correlation. So we're going to go to table 7.9. Turbulent flow for a local correlation for the Nusselt number. 0.0296 Reynolds numbers to the 4/5, Prandtl number to the 1/3. So this is the correlation that I've written down here. Please do take the time to communicate which correlation you're using in your solution. Write down the correlation. So we're going to do the same thing. Substitute in 40 centimeters now for the Reynolds number and here for X, and we'll get 84.36 watts per meter squared K for H. So in the turbulent region, H is higher than in the laminar region. That's not always the case, but for smaller X values that's the case, because remember that as you move farther down the plate, so as X increases, H is also going to decrease in the laminar region and also in the turbulent region. So if you're far enough from the leading edge, even in the turbulent region, you might end up with an H low enough to be comparable to the laminar case. But this is what we would expect for moderate values of H, that the turbulent case, H is larger than for the laminar case. Okay, so continuing on, considering we need the average heat transfer coefficient over a length of plate of 40 centimeters, and so that's going to be mixed flow. Right, up to about 30 centimeters it's laminar, and then it's turbulent for like the last 1/4 of the length. So in that case we're going to use an average correlation. So that correlation for mixed flow in this case, reading that off of the chart, table 7.9, mixed flow is here. So that's the correlation that I'm using to the 4/5. This little minus 871 accounts for the laminar region. We've already talked about this correlation previously. So we're just going to use that correlation. So Reynolds number at L, 40 centimeters, if you substitute into the definition of the Reynolds number, 6.838 times 10 to the 5th, so this goes here. The Nusselt number goes there, solve that for H, we get 52.12 watts per meter squared K. So that's the average. So the previous H values were the local values at particular locations. This is the average over the length from the leading edge, X equal to 0, until L. But we need the average so that we can compute the heat transfer. Q is equal to H times temperature difference times the area. So length times width into the page, and you'll end up with 103.2 watts. Let's continue on to another example. Flat plate, subject to parallel flow on the top and the bottom this time. The flow is coming in at 5 meters per second. T ambient is 20 degrees C. We're going to compare the case of air flow to water flow. We're going to get the heat transfer coefficient and the convective heat transfer rate when the length of the plate is 2 meters long and W into the page is 2 meters and the surface temperature is 60 degrees C. So again, I'll just show you my solution. So in this case we have flow of either air or water, so we're going to work the problem twice effectively on the top and the bottom of the plate. The plate is at 60 degrees C, the ambient fluid is at 20 degrees C, the length of the plate is 2 meters, and the width in and out of the page is 2 meters. So in order to get, so we need the average heat transfer coefficient, which will then be used to calculate the convection. We're going to do it for air and again for water. So the first thing we're going to do is go get the appropriate properties. So we need the film temperature. So the average between the ambient and the surface is 40 degrees C, so 313 K. So do our interpolations for air. We're going to go back to table A4. So here's a Nusselt number. I'm sorry, a kinematic viscosity and the Prandtl number. We're also going to need K. I didn't use that. I didn't go get that until later. I guess I could add K to that. And then for water, you're going to go to table A6. Table A6 is the saturated liquid water tables, actually the saturation tables, but it also gives you viscosity and Prandtl number and density. Well, it gives you specific volume, so you have to know that density is 1 over specific volume. It doesn't give you kinematic viscosity directly, so you need to go get the dynamic viscosity mu, divide that by rho. It does give you a Prandtl number directly. So all of these are the saturated liquid values. The table also gives you saturated vapor values, but we're using the liquid values. Make sure you're going to use the liquid values for that. Okay, so that gives us a value for kinematic viscosity for the water. Okay, so the next question is going to be, is the flow laminar or turbulent or mixed? What is the situation? And so what I did is I calculated the Reynolds number at the end of the plate. So for the air, that comes out to be, so use nu of air here, that comes out to be 5.815 times 10 to the fifth. So just barely larger than 5 times 10 to the fifth. So this is going to be a mixed situation. Most of the flow over the plate is going to be laminar, but there will be a small region at the end that's turbulent, so we'll use mixed flow there. The Reynolds number for the water, so use the water kinematic viscosity here, 1.511 times 10 to the 7th. So a much larger portion of the plate is going to be turbulent, but this is still a mixed flow situation for both. So we're going to use the same correlation, that for mixed flow. So we'll go back to mixed flow, the average. So I'm using this correlation from the table. Again, that 871, that minus 871 is accounting for the laminar region. If we didn't have a laminar region, that can just be crossed out, but we do have a laminar region here. Okay, so that's our correlation that we're going to use. So for air, I'm going to use the Reynolds number calculated above and substitute that here to give me a Nusselt number. That comes out to be 571.3. And then the Nusselt number is defined as K times L over, H times L over K. So solve this for H bar, so we're going to end up with a Nusselt number times K over L. So I need, this is the interpolated value for air thermal conductivity. So we end up with a H bar of 7.8. So then we can substitute H bar to calculate the convection. So Newton's law of cooling is H times delta T times, this is the area, and then we just have to remember there's two sides of the plate in this case. So we end up with about 2.5 kilowatts for the air situation, H being 7.8. For the water, so different Reynolds number goes here. That for the water we need K for the saturated liquid case. So that comes from table A6. Calculate H again, and we'll get about 10,000. Much larger, right? 3 orders of magnitude larger. And so then the resulting Q in this case is 3 orders of magnitude larger as well. So 3247 kilowatts. Okay, so you would expect water to provide a much higher cooling rate and have a much higher heat transfer coefficient than for the air. Let's consider one more example. Something that's a little bit more complicated. So in this situation, we have a flat plate. They're trying to maintain a uniform surface temperature by controlling the power at different lengths along the way. So what they've done is they've broken up the plate into small little modules. Each module is isolated, so there's insulation between the module, insulation on the bottom, and so each of these little modules are now controlled, and so a voltage times a current, for example, is providing energy into this module, which is then dictating what's the flux coming out of this surface. So they've got a control system set up that maintains the temperature to be isothermal. So they're controlling the power output of each one of these modules to keep the surface for each one of these modules at 150 degrees C. So what is it? Is it air? Modules. Atmospheric air is flowing over, comes in at 25 degrees C at 30 meters per second. So it's asking us to find the required power generation inside each of these modules. Alright, so the power generation is per unit volume. So take this power times the volume of the module. That power generation times the volume of the module, that's going to balance to equal the flux leaving. That's got to balance the convection. And then it wants us to also in part B find the maximum temperature. So I'll talk about that a little bit later. Let's just focus on this one. To find the power, we need to first find the convection leaving each module. They're only concerned about one particular module, one module that is 700 millimeters from the leading edge, and then the length of each module is 50 millimeters. So again, I'll just talk through my solution that I've already written out. So we have a module here that is 0.7 meters away from the leading edge. Length of that module, I'll call that B. 0.05, that was 50 millimeters. There's actually a thickness of this A up here is 10 millimeters. I don't have shown here. We won't need that until part B. 150 degrees C on the surface, 25 degrees C for air flowing over this. What we want to find out is what is Q convection for this module. So only from X equal to L to X equal to L plus B. We need that average over just that module. W into the page is 1 meter. So we're going to come up with this first, and then with an energy balance of the module, Q dot times the volume of the module equals that convection that's leaving. The volume of the module is just B times this length A times W into the page. So we can calculate that Q that needs to be generated for that convection rate. So we're going to come up with Q mod first, that convection part. Okay, so first thing, to continue to get that H bar, we need to know the film temperature. So that's the average between the 25 and the 150, so 87.5, so 361 K. Go to table for air, go to table A4, and interpolate to come up with these values. Don't forget the times 10 to the minus 6 for the kinematic viscosity and 10 to the minus 3 on the Ks, on the properties, thermal conductivity. I'm going to calculate what is the critical length. So where does it transition to turbulent? So Reynolds number is equal to 5 times 10 to the 5th. Solve that for x of c. Nu over velocity. That comes out to be, I think we've already done a problem with these numbers, very, very similar. This comes out to be 292 millimeters. Okay, so or 0.3. So in comparison to this 0.7 up here, at about 0.3, so at about almost 1/2 of the way through, we transition to turbulence. So we transition to turbulence here, so the module is well inside the turbulent region. So to come up with, so we need to get this H bar now so we can calculate the convection. So this is the average only over the module, so from L to L plus 1. So by definition of average, that would be the integral from L to L plus B, not 1 but B, of H dx divided by the length from L to B, from L to L plus B, so the length is B. 1 over B, integral from L to L plus B of H. How do we come up with H? We need the appropriate correlation. So for turbulent flow, the Nusselt number correlation is this. So copy this from table 7.9. Do communicate this. What we're going to do is solve this for h, right? The Nusselt number is h times x over k. Solve this for h, so this h is going to be k over x here times the Nusselt number. And then the Reynolds number is, inside this correlation, is u times x over nu, so that's to the 4/5 power. So there's an x dependence in this h here in the denominator, and then also x to the 4/5. Everything else is a constant. So what we're going to do next is just evaluate that interval. So I have everything substituted now for h into the interval. Take all the constants out front. The only thing that's left to depend on x is this x to the -1 and that x to the 4/5. The end result is x to the 1/5 that we're going to integrate. It's kind of interesting that this 1 over x kind of cancels the integration. It adds that power of x right back. So anyway, so we're going to have now x to the 1/5, integrate this, and you'll end up with x to the 4/5. So we return to that same power that's in the correlation, 4/5 divided by 4/5. So I have 5/4 times x to the 4/5. So this is evaluated from L to L plus B. Alright, so L plus B gets substituted, and then L. So this 5/5, this part of the answer accounts for that interval. And these are all the constants out front. Okay, so at this point, we have numerical values for all of these. We can just substitute directly, and we'll end up with h bar is equal to 75 watts per meter squared K. So we can now take that, let's go on down, skip my little discussion here for now, go on down and calculate the convection is h bar times temperature difference times the area. So B times W is the area, right? So we go back to the drawing. The area is this length B this way times W in and out of the page. So we end up with 468.8 watts. Divide that by the volume to get the power generation needed. So we end up with, in terms of meters squared, a pretty large number, 9.376 times 10 to the 5th. Okay, so this is the number we'll need to start talking about the solution of part 3. But before we move on to that, let's go back and look at this. We had just finished the integration, and now we can substitute in numbers for that to get that h bar. We can also kind of look at this and recognize that now that I'm returned to powers of 4/5, and that's a power of 4/5 there that can be distributed, we can very easily convert this back to be expressed in terms of a Reynolds number to the 4/5 power. Alright, so let's do combine this u over nu to the 4/5 with each of these, distribute that through, and that'll turn those into Reynolds numbers. I'm going to factor out that Prandtl number, and then all of this combined equals 0.037. So it turns out that it can be expressed in terms of, these are Nusselt numbers. In fact, if you go look at table 7.9 again, the Nusselt number for mixed flow, 0.037, Reynolds number to the 4/5 power times that Prandtl. So omitting this minus 0.871, right, that is the correlation. And since we're doing a difference between these two, the 871 is going to cancel anyway. So it turns out that you could actually get the Nusselt number at L plus B, the average, minus that at L, and then back calculate the solve for h bar. So that's an equivalent way to do it. However, this is not obvious, at least to me, without going through and making these observations. So I'm going to ask you, don't start with this. Don't use this because it's not obvious in this case. What I'm going to ask you to do is evaluate this interval. Set up the interval for h bar and evaluate that way. Okay, so let's move on to discuss part B. Part B is saying find the maximum temperature in the heat generating module. So now looking inside this module, right, there's a surface temperature, but since we have generation throughout this volume, there'll be a higher temperature on the other side. So this goes back to, I forget which chapter it is where we talked about generation. I think it's chapter 3. There was some discussion of heat transfer with generation, right? So we got to go all the way back to that. Now remember, when you have a situation with generation, you can't assume a linear distribution, so you actually have to solve a differential equation. So there's kind of a lot to think about for that problem. So I have some notes for that as well. Actually, you know what? I'm going to actually write the solution out for that one. I'll take time to go through that instead of just showing you what I've written over here. So this is for part B. I'm going to draw the module. So this is our module. It's insulated around the outside. So inside this region here we have a Q dot. And remember, that was a distance A. That's a distance B. W is into the page. Okay, so we have a temperature. That's 150 degrees C on the surface, and we also know that Q leaving through convection, what was our number? Comes out to be, looking at the wrong problem, just 1 second. For 68.8 watts is leaving, and Q is equal to 9.376 times 10 to the 5 watts per meter squared. That's a 7. Okay, so the temperature will increase throughout this thickness, so T max is going to occur on this side. So this is analogous to a wall situation with generation inside the wall. So if we were to look at this from a side plot, let's say X is going this way, this is A on the other side, this is the insulated wall on the back side where T max occurs, temperature drops as we come out here, so there is T surface is equal to 150 degrees C on this side, and there is T max. So the question is, what is this temperature on the other side? This is considered insulated. Okay, so we need to actually solve the heat equation with generation very quickly inside this material. Alright, so inside that material, K is equal to 5.2 watts per meter K is given to us for that material. So we'll start with the heat equation. K times the Laplacian of T plus Q dot is equal to rho C sub P partial of T with respect to time, except this is steady. So we don't have that storage term on the right hand side. We do have that. That's going to stick around. That, we're going to use a 1D version for that. So we're going to end up with K times the second derivative of T with respect to X plus Q dot is equal to 0. So this is our governing differential equation that we can solve. Those are constants. We can solve for T. Right, so dt dx squared is equal to minus Q dot over K. Integrate once puts an x here plus an arbitrary constant. Integrate again. We'll end up with minus Q dot over K 1/2 x squared plus that first constant times x plus a second constant. Let's call those constants 1 and 2. Now we need those constants, right? So we're going to apply boundary conditions to figure those constants. This is T as a function of x. So at x equal to 0, right, we have a 0 slope over here. At x equal to 0, dt dx is equal to 0. So take a derivative of this, and we'll end up with minus k minus a constant q dot over k times x plus c1 is equal to 0 at x. So let's go ahead and write it out there. Minus q dot over k times x plus c1 is the derivative. I'm going to evaluate that at x equal to 0, so this disappears, and that's equal to 0. Okay, so this boundary condition is going to say that c1 is equal to 0. So that takes care of the first one. Alright, for the second boundary condition at x equal to a on the other side, the temperature, so the temperature at a, we substitute in a for x, is equal to 150. So T surface. So let's take a and substitute that into our equation above. T at a is equal to minus q dot over k 1/2 a squared. That's the first term. That was 0. Plus C2. This has to be equal to TS. So that gives us an expression for C2. C2 is now equal to TS plus Q dot over K 1/2 A squared. Okay, so if we use that above in this equation, right, if I substitute in A here, that'll give me the max temperature. Well, I'll go ahead and make the substitution. Let's take this and put it in place for C2 there. We'll end up with T as a function of x is equal to minus Q dot over K 1/2 x squared plus C2, so plus this Q dot over K 1/2 A squared plus TS. I swapped the order of those two. So there's the temperature profile. So the maximum value occurs at x equal to a. T max equals T at 0, not at a, at 0. On the left hand side where the maximum occurs. So that's equal to that C2, or this. So Q dot over K 1/2 A squared plus TS. So now we can just substitute in numbers. If you evaluate that, you get about 9.02 K. Add that to the 150, you get 159 degrees C is the maximum temperature. So part B really wasn't associated with convection, but took us back to review a little bit of previous topics that dealt with generation inside a flat plate or a wall, plain wall. Okay, that concludes my examples that I'm going to work. I'll do another lecture that's going to talk about a little bit more theory, just dealing with it. It won't take long to talk about convection around different shapes like flow, external flow around a cylinder or a sphere. We'll talk about those correlations, and I'll work one example with those. And then I'll talk about the solution for some of the other problems that have been on the test. And we can even talk about the last two problems in the sample exam problem handout that I've given you that I call challenge problems.